Hello everyone, my name is Paul Carneau. I'm a structural engineer and PhD student at Navy Laboratory in the École des Ponts et Chaussées in Paris. I'm going to talk about the characterization of the layer pressing strategy for concrete 3D printing. This research is part of my PhD on concrete 3D printing of cantilever and form finding of printable geometries in general, for which I'm supervised by Olivier Baverel, Nicolas Roussel and Romain Mesnil. All the experiments are done in our 3D printing cell with a 6-axis robotic arm equipped with an extrusion head developed by X3 and controlled with HAL robotic software, our industrial partners. I started my PhD by comparing 3D printing and masonry structures in order to see if we can get insight on how to build cantilever in additive manufacturing following ancestral masonry techniques. One main result of this work was that to ensure a successful print, we have to look at the stability of the printed object at 3 different scales: the scale of the final structure, the scale of the temporary structure being printed, and a local scale corresponding to what's happening at the extrusion nozzle of a single layer. This last scale is the subject of this presentation. Different extrusion-based strategies for additive manufacturing are used within the community today. We are interested here in the layer pressing strategy, illustrated on the right, where the extruded material has a low initial yield stress that allows us to shape the layer's cross-section on the go. We can indeed modify the geometry of the cross-section of the layer independently from the nozzle diameter and always keep a good control over the layer position. This allows us, for instance, to print with variable inclination, as you can see on this example of a barrel vault 3D printed without temporary supports. So to start, let me introduce you the printing parameters involved during the extrusion. We have the printing velocity VR, or the speed at which the nozzle is moving, the extrusion speed VE, at which the material is extruded, the nozzle diameter D, and the layer's cross-section geometry defined by its width B and thickness H. Those parameters are related by the following expression of mass conservation. In the layer pressing strategy, H is given by the position of the nozzle, and the width B is a result of the imposed velocities. Whereas in the infinite block extrusion, the layer geometry is directly given by the shape of the nozzle, and in the case of the free flow deposition, the layer geometry is a result of the competition between gravity and the material yield stress. With this relation in mind, we first performed a parametric study in order to understand what are the range of admissible parameters that we can use for the extrusion. We printed multiple square towers of 10 layers each, with variable thickness, printing speed, extrusion flow rate, and length of the object. That allowed us to identify different printing regimes. The first one is the ideal regime, where we have a perfect control over both the width B and the height H of all the layers. For high printing velocities, we started to observe some longitudinal tearing of the layers. This failure mode can be related to the ratio between the printing velocity and the extrusion flow rate, which creates the longitudinal strains leading to the tearing. We identified this regime but haven't studied it in detail so far, and it is not in the scope of this presentation. The third regime is well known and corresponds to the case where the thickness of the layer is too high for the material to withstand its own weight. The layer flows on itself, leading to accumulated error on both height and width of the entire structure, leading eventually to its collapse. Finally, the last regime appearing for small layer thicknesses corresponds to an overpressing of the sublayers by the extruded material. When a nozzle passes above all the layers, they are deformed, leading to this pyramidal cross-section. Note that the total height of the structure is still controlled. And this phenomenon doesn't automatically lead to a failure of the structures, as we can see on this example of a twisted tower, where the pressing phenomenon appears on the corners. Our goal in this research is thus to find the parameters range that ensure a pressing of the layer to keep a good control over the layer thickness, but without overpressing them to avoid deformation of the sublayers. So we first define an upper bound condition for the layer pressing strategy involving geometric and kinematic parameters. We introduce a characteristic time, Tc, corresponding to the time that the nozzle spans above a certain section of the extruded layer. Tc can be seen as the pressing duration. And we can relate it to a cylinder of material in the nozzle, whose length is given by this characteristic time and the flow rate. It results that the layer will be pressed if the height h is smaller than this characteristic length Lc. And we can rewrite this relation using printing parameters only to get our upper bound condition for pressing layers. Our second objective is to identify the force created when we are pressing layers. To do so, we developed an experimental protocol where layers of different thicknesses are extruded on a balance. We repeated the experience with different flow rates and initial yield stress of the material. And we can retrieve the data, giving us the weight of the material and the additional extrusion force that can be directly detected on the graph by the jumps before and after the plateau. After some post-processing, where we remove the weight of the material from the data, we can plot the force we are interested in function of the thickness of the layer. We observe the same tendency for all the different cases, where the force increases significantly when the layers get thinner. And we can compare the value of this force in blue to a force in gray equivalent to the layer's weight, which increases linearly with the thickness. We can see that the two curves have opposite slopes and that for small values of h, the pressing force can be up to 10 times higher than the layer's weight. It confirms that we need to take this phenomenon into account when setting the printing parameters. To go further, we propose an analytical solution for this force depending on the printing parameters and the material properties. We started from a known relation giving the force necessary to deform a longitudinal lace of length L and yield stress τ0. And we apply the same relation to the case of a 3D printing process, simply by recalculating an equivalent length, L equivalent, in function of the printing parameters VR and VE, giving us our new relation for the force in the case of 3D printing. And we can see a good fit of this analytical relation with the experimental results, with some discrepancies when the layers get thinner and the force higher. From this, our final objective is to map the different printing regimes observed in function of the printing parameters. We still need to define the lower bound for pressing layer by writing a stability condition on the layer N-1, the first sublayer. We can calculate this layer's yield stress at the time that the new one is printed above it by this relation where we introduce the structuration rate at x, and we can write the condition that prevents deformation of this layer N-1 by stating that the material resistance must be higher than the stress coming from the weight of the layers and the additional pressing force that we have identified before. We finally have our lower bound condition on layer N-1 given by this relation, and we can see that this is expressed by the same parameters that are involved, the parameters that define layer N. All the printing regimes can be grouped on a single diagram in function of adimensional parameters h star, which represent the layer thickness divided by the nozzle diameter, and the velocity ratio v star equals to the printing speed divided by the extrusion speed. In this diagram, the frontiers of the control pressing regime in blue are defined by the upper and lower bound pressing conditions that we have introduced before. We can see in yellow the upper bound and in dark blue the lower bound between the control pressing and the overpressing of the layers. When preparing a print, the parameters can be set using this diagram to ensure that we will remain in the correct printing regimes at all times, even if the layer's cross-section changes. This concludes my presentation. For more information, you can visit the built-in website or follow us on ThinkShell. Thank you for your attention.